Hello, everyone. Welcome back to another episode of Computer Vision Talks. And today we have with us Chirag. I'll start with the introduction because that is quite interesting, and we'll be asking a few questions around the cool work he does towards the end of the talk. So, Chirag is a research scientist at Adobe and a research affiliate at Harvard University. His research interest includes developing trustworthy machine learning that goes beyond training models for specific downstream tasks and ensuring that they satisfy their other desirable properties such as explainability, fairness, and robustness. He is also one of the co-founders of the Trustworthy ML Initiative, which is a forum and a seminar series related to trustworthy ML. He's also a very active member of the machine learning collective research group that focuses on democratizing research by supporting open collaborations in ML. So I think that's how I found Chirag in the first place. He shared his paper on Twitter, which was done under an open collaboration from ML Collective Initiative. And I was super intrigued and I wanted to talk more about the paper because it's really impactful. And also, an open collaboration is what we are aiming at the end of our journey, right? So over to you, Chirag. Let's get started and let's talk about your work that was accepted at CVPR.
Thanks, Shambhavi, for the kind introduction. So, hi everyone. Today we'll be talking about the impact of estimating example difficulty. So, as Shambhavi mentioned, it will comprise of the majority of the talk will be about the CVPR paper that got accepted last year, and towards the end we'll also be talking about how can we actually go further after we have identified these hard samples, right? So. The overview of today's talk will be, I will start with a small motivation. Then we'll be talking about estimating hard training subsets. How can we actually estimate them and identify them correctly? And finally, we'll be talking about the impact of hard subsets in a transfer learning setting. I'll be happy if there are questions in the middle, and yeah, I'll be glad to answer them on the fly. Great. So I don't think I need to say this more, but machine learning models are being deployed to a wide range of real-world high-stake applications, going from healthcare systems to military, finance, social accommodations, and the list goes on. One thing that we are missing is that it is very important for both the model developers and practitioners to actually understand what the model is thinking before we trust them with these high-stake decision-making. In addition, model understanding is also critical in several domains, especially in these high-stakes ones. And given the availability of millions of data points, understanding the role of easy and hard examples during the training can help us train better and faster models, essentially. So that basically brings us to the first question that we'll be talking in today's discussion. How do we estimate hard examples? So before we go into that question, I'll just like to give a very brief 101 on explainable artificial intelligence, as that would basically build the foundation of our talk. So explainable AI is basically referred to as a set of algorithms that provide a description of the behavior of a very complex machine learning model. Now, we can come up with an explanation for a simple linear model or a very complex deep neural network model, but essentially it is a set of algorithms that provide a description. This description can be in the visual space, can be in the language space, but it's some kind of description. So let us take an example. So we have an image of a husky with the background of snow. We send this image to a black box image classification model. Let's pick ResNet. And the model misclassifies this image as a wolf with 98% confidence. Now, it is very unintuitive for us to understand that how can this image be misclassified as a wolf, because the husky is clearly visible and it's almost comprises of 70% of the image, right? So these type of misclassification actually drives the whole research of XAI, such that we actually understand what the model is thinking. So if we take vanilla lime algorithm, which is one of the widely used explanation method, then it basically says that the model was focusing on these snow regions in the image rather than on the dog itself, right? So this basically says that the whole 98% confidence that the model was predicting this image as a wolf was attributed these to these background snows. This actually gives us a lot of insights about how the model learns about this husky versus wolf classification. So if we take some more examples, then you would see clearly that images where there was wolf, it was correctly classified as this background was snow. And even the images of husky on a non-snow backgrounds were predicted clearly. But only the images of husky with a snow background were misclassified. So if we have to do like a TLDR on this classification task, then we can say that the model was basically biasing its decision of wolf versus non-wolf by just seeing whether the image had a snow background or not, right? So this kind of debugging the model is one of the primary tasks of explainable AI also. So this brings us to different methods of how can we come up with explanations, right? So one of the widely used category of explanation methods are gradient-based methods. So gradient-based methods and their variants are plenty in the whole XAI field. But one thing that has been observed is the vanilla gradients of a model, which is basically taking the gradient of the model with respect to the input, is very noisy and unintuitive. So if you look at this image, you can still see that the high attributed gradients were focused more or less on the dog, but it's very noisy. So in order to alleviate this problem, there have been people have proposed a lot of different methods like smooth grad, guided backpropagation, integrated gradients. All these are like some variants of gradient-based methods in order to smoothen out these gradients and to come up with better explanation maps, right? As you can see, smooth grad presents a very like unnoisy version of gradient methods. And if you see, if you look at the heat maps generated by integrated grad, then it basically tries to segment the dog in some sense, right? So in this particular paper, we actually don't build using these high like approximation gradient-based methods. What we do is we take a step back, and when we try to understand whether just using raw vanilla gradients, which are noisy, because that is the gradient is the actual information that the model was using to train on the downstream task, right? So we try to use that raw vanilla gradients and question that whether that gradients are sufficient enough to understand the model's training dynamics, and then use that for assessing the interpretability, right? So the simple hypothesis that we had when we started this work was that gradients of easier examples would converge quickly and early on in the training, whereas gradients from challenging examples or hard examples will continue to vary throughout the training. You can look at it from a different point of view, that if a model is confident of training or classifying a given image, then the gradients or the backpropagation laws generated for that particular input will be saturated as the training progresses. But if the model is not confident about a particular image, then the gradients will keep on fluctuating till the model converges, right? So that's like the basic hypothesis that we used. To validate this, what we do is we define a very simple proxy metric that we call as variance of gradients. We'll be talking about that in the later slides. But to understand how to calculate variance of gradients, let's take an image. So most of the image classification models are trained on a RGB image, let's say of dimension 32 cross 32 cross 3. The way we generate gradients is we take the back propagation and we then take the channel average gradients so that we convert the gradient image into a 32 cross 32, right? So we basically take the gradients for each of the channels, RGB, and then we average them out and get a single 32 cross 32 gradient map for each image. This we denote as S. Great. Then what we essentially do in variance of gradients is we capture the channel average gradients that we talked about in the previous slide, and we aggregate them over k different checkpoints. Now, checkpoints, I guess it's a widely common term. What I mean by checkpoints is that as the training progresses for a given model, we store the intermediate weights at different checkpoints. It's a 5, 10, 5, 6, 7 epochs, for instance. So we store the gradients for each of these 3 epochs for all the images during the training, right? What we then do is that we collect these gradients, as I mentioned, for different checkpoints. And as you can guess, for different checkpoints, the gradients will evolve as the model is getting more and more confident or less confident for some or the other images. We then basically calculate the variance of gradients using these checkpoints. So let's say, let's go through the formulas. So let's say we choose K checkpoints during the training dynamics. This can be as simple as like the first 3 epochs of your training, right? What we then do is we calculate the gradient for each image for these 3 checkpoints. And then we calculate the mean gradient that's denoted by mu. We then basically calculate the VOG pixel per pixel, because as I mentioned in the previous slide, we'll be getting a 32 cross 32 image as gradients for each checkpoint, right? So we basically get 3 different 32 cross 32 gradient maps. We then basically calculate the pixel-wise variance for all these gradient images. So technically, the output of this VOGP will be, again, one 32 cross 32 map, which basically represents the variance of each pixel. What we then do is we basically take the mean of the VOGP using n. N basically determines the total number of pixels in the image. So in this running example, it will be 32 times 32, right? So we do this, and then we the VOG is basically a scalar metric, a scalar score. So for each image, we'll be getting one scalar score, which we define as VOG. It would be great if there are any questions for organic metric, as we'll be using this to build our follow-up slides.
I don't see a question in the chat box. However, I do have a question. When you talk about storing the checkpoints for all the training images, how much memory does it consume?
Exactly. So I think that's a great question, Shambhavi, and that was one of the bottlenecks of this approach, because as you can imagine, if you take a large data set like having million of images, then it would be very hard to store those gradients, right? So that is why that is one problem. And in order to solve that, what we basically showed in this work is we can approximate correctly the VOG scores by using as small as 3 epochs. So even if you calculate the VOG score using just 3 epochs during the training, you can actually come up with a good approximation of the easy and hard easy and hard examples. But yeah, I agree. The computation is one of the challenges. And just one more point to that, and that was also one of the reasons why we did the averaged gradients across the channel, because as you can see, otherwise we had to store like this times 3 number of gradients. So yeah.
There's a question from Avi, and I think Nikhil was also unmuting himself. I'll just take the advantage of being posted to ask one more question before I let you unmute yourself, Avi, if you want to, if you want me to unmute you. So the last question I had was, when we talk about just using 3 epochs to compute this gradient or average out these gradients, do we also follow some kind of constraining policy to have the samples that were tough to align the gradients to the ones that are so easy? Because if they belong to the same class, one method could be constraining the gradients to alignment.
Right. So we don't do that. That is basically what we get as an output from the VOG scores after we sort them. We are able to actually get the hard and easy examples as we basically like take the insights of the VOG scores and sort them and create buckets. Like we see that examples having high VOG scores are the ones usually that are harder examples, right? And vice versa. So we don't do that during the calculation of the VOG scores per se.
Okay, so hi. Firstly, before I ask my question, I was having some issue with the chat. Maybe the chat is disabled from my end, or is it for everybody?
Okay.
And going to the question. What?
Sorry, I'm just asking Nikki to fix that. Yeah, please go ahead with your question.
Yeah, I think mistake.
Okay, so in the question, like the image that I'm saying 32 cross 32 cross 3, the image would be the salient image because the background is completely blurred and the object would be the highlight of the image. And like if there are multiple objects on the image, how would it impact the variance of the gradient part? Hello?
Yeah, I can hear you, but
okay, I think he has like
I think Nikhil, can you hear us?
Yeah, I can hear you, but I'm not able to
I
hear
think yeah,
Chirag.
there is some internet issue with Chirag's question. Chirag's on Chirag's end. Can you ask your question again? Probably just as soon as he joins back.
I think his video is freeze, so like
Yeah.
we'll wait for a minute.
Okay, I'll pause the record.
Input image that we are providing, the image is 32 cross 32 cross 3 RGB image. So the object need to be highlighted in the form of salient because the background is blurred. And secondly, like if there are multiple objects in the image, how would it like display the gradient part?
That's a great point, Avi. So one thing that we observed is that we don't make any approximations on the image. The underlying hypothesis is that whatever the model feels about this particular image, that it gets the information of that, but we get using the gradients of the model, right? So if the model in this particular image, the image of the bird, the model was confident about localizing the bird in the first few epochs itself. So we got these localized gradients around the bird, but it's not necessary that we will be getting this for all the images. Going back to images comprising of multiple objects. So we'll be seeing some examples in the following slides. But again, most of the image classification models, we basically have one labels, right? And the backpropagation that usually happens is on that particular label. So the gradients are actually directed towards the targeted object in that case. So we still see that the gradients are on the object itself.
Okay, so because like if we consider this particular image and we have the ground truth of the image, and could we like with the specific gradients, can we segment out the object out of using the like keeping ground truth as the another image and reducing the loss at every epoch? So will it be possible?
Yes, sure. You can do that. You can surely do that. But that's like another prior information that you'll be using for training the model, right? So what you're essentially saying is that I take the image and I take its segmentation mask so that I can tell the model to focus on just this region to classify this particular image into this class, right?
Okay. Hmm.
Great.
Okay.
I hope that
Thank you.
answers your question, Avi. There are some more questions in the chat box. So I'll read them. I think you partly answered this one as well. So Karthik is asking, could you please give some insights on what do you mean by gradients getting converged?
Sure. So yeah, that's a great point. So what I basically mean is, I'll take a simple toy example. Let's say essentially what image classification models are trained on is get under cross entropy loss, right? What we basically do during the training is we calculate the cross entropy loss at each epoch, then we backpropagate that loss, right? And the gradients are basically proportional to the loss, right? As the model converges, the loss becomes slow and the gradients starts converging so that there are no more updates on the weights of the model, right? In the perspective of these images and VOGs, what we basically say is for samples where the model is confident, it won't backpropagate large gradients for them because the gradients are already saturated. So it doesn't mean that the gradients will be large or small. It basically means that gradient will be saturated, right? So they won't fluctuate anymore because the loss for that particular image is fixed now. The model has learned that image. And that is what we basically mean by gradients getting converged.
Great. I hope that answers your question, Karthik. The next one is from Jamal. He's asking, why do you store the per pixel gradients? Shouldn't this be sufficient to store the average gradients over the...
So these particular equations were just to show the actual simplification, how we get to the scalar score. But in the code wise, if you talk about, then we don't actually store per pixel gradients, right? We just store this scalar numbers, that's it. And also, I'll add one more point, and this goes back to the questions, Shambi, that you asked. We are not actually storing the gradients. We are actually just storing the weights, right? So the training keeps progressing. We just store the checkpoints or the weights of the model during like some definite checkpoints, right? And then we are basically doing it in a different setup. We just load the weights of the model again, and then we calculate these gradients. So it's not necessary that you have to do it on the fly during the training. So I hope that that is clear now.
And when you mentioned that you don't have to do it on the fly during the training, that I have another question around that. Have you observed the behavior of these gradient saturation during eval? Like in eval,
Mhm.
also most of your layers are working, like batch norms and everything, just the dropout
Correct.
and some of the parameters at least.
Correct. So we also tested this on the like the test set or the evaluation set, and I can come to that. There is a slide where we talk about it. So, but yeah, to briefly answer that question, it works even for the eval stage.
Interesting. Okay, great. Last question before we move forward. How are you deciding to scale checkpoints? There's a question.
So that's like a hyperparameter choice, to be transparent, because and it also is dependent on the data set itself, because like for easier data sets like CIFAR 10, you can see the model is getting confident and it reaches some 40-50% accuracy even in the first 3 or 4 epochs. So we found out that even using just the first 3 epochs to calculate VOG scores is sufficient enough, right? But the 3 epochs that I mentioned is consistent for data sets ranging from CIFAR 10 to MHNet.
Okay, perfect.
So, hi, Chirag. Yeah, I have a question. So, in the ST initial epochs, the model is not doing well. So the gradients can be very noisy, right? So if you give equal importance to all the epochs, so the initial epochs will have a noisy gradients, right? So does that that will automatically impact the VOG, right?
Exactly. And that's why I mentioned that it's dependent on the data set. As I said, for CIFAR 10, the model actually gets a lot of good prediction accuracy, around 30-40%, even in the first 3 epochs. So it shows like the just epoch 1, 2, 3 for CIFAR 10, for instance. But for ImageNet kind of data sets where the model takes time to train, we basically took epochs further during the training. The running condition that we were using to choose these checkpoints are essentially whether when the model is at least confident that it has achieved accuracy better than random guess. And then we start calculating and using these checkpoints.
So, but during test time, we don't have this access to accuracy, right? We don't know the accuracy during test. So how this will?
And so for test time, I agree on truth label. We can just use the top 1 predicted label as the model is predicting for test set. So, and then basically backpropagate the gradient using the top 1 predicted label, and that also works.
Yeah, like using them as hard pseudo labels. Okay, great. Those were a lot of questions. Let's move ahead with the talk.
Sure. Thanks. So yeah, I'd now like to just briefly talk about a toy example that we used to basically motivate the importance of VOG. So in this particular figure, you'll see we just use a simple Gaussian data set and we trained a linear model. The yellow and purple are basically 2 classes. All the blue and red points are correctly classified to both the classes, right? Now, I just like to recap what I said in my previous slide. VOG essentially says that points which are close, for which the model is more confident, the VOG scores will be small. And for harder examples, the VOG scores will be high, right? So we took that hypothesis and then we plotted this figure where we basically have the VOG scores in the x-axis, and we had the perpendicular distance of the points that you see on the left from the decision boundary on the y-axis. So as you can see, for a linear problem like this, points that are near the decision boundary, the model, those are hard examples because that is where the confidence usually decreases. But for samples which are further away from the decision boundary, the model can easily classify them. So we actually see the same insights in this figure, where we see that for samples where the perpendicular distance from the decision boundaries were high, they had very low VOG scores. And as the VOG score increased, the perpendicular distance of these points from the decision boundary kept decreasing. So that's the, that was like a toy examples experiment that we did to motivate the use of VOG. Great. So now I'll be moving to some results, and I'll be essentially talking about all the different tasks that you can do using VOG. It's not just like a debugging tool to identify easy and hard subsets, but it can also be used for several other analytical insights. So in this first example, what we see is we look at the results from one of the experiments where we train a ResNet 18 classification model on the CFAR 100 dataset. And when we calculated the VOG scores, and then we showed how the easier and harder examples vary from the early to the late stage of the training. What we see here is that there's a stark difference in the images having low VOG scores and high VOG scores. We see that early on, images having low VOG scores are mostly centered and consist of typical images of the class like red apples, whereas images having high VOG scores are often cluttered and they are taken from different vantage points. Here you can also see that VOG can uncover like some kind of a color bias from the model, where the model was more confident in learning red apples than like green and yellow apples, for instance. Great. So then we'll move to task 2. Here we basically show that how can VOG be used to relatively rank a given class and its different images, right? So VOG only, as I said before, VOG only requires gradients, which are already calculated during the training. So we can actually also use this analysis to get some insights for large data sets like ImageNet. So what we show here is that if you rank the images for a given class, let's say the magpie or the pop bottle class, by their VOG scores relative to their class, then the low VOG scores contain objects which are usually centered, like in the magpie class, if you see, the lowest VOG scores are always for images where the magpie is on the center, in the center of the image and has a very clean and simple background. Whereas images with high VOG scores are basically comprising of magpie images where the bird is zoomed in, or there are some augmented versions of the bird, right? And the same thing is observed even for the pop bottle class, where the lowest VOG scores basically comprises of like classical images that you can find of pop bottles, like a stack of bottles. But the highest VOG class basically comprises of images where the bottle is zoomed in or occluded, or basically taken from some different vantage points. So this can be actually used to also understand like very big, large data sets like ImageNet. Any questions?
None.
Okay,
I think
great.
we can proceed.
Great. So one of the interesting things that we observed from VOG is that it can also be used to analyze misclassification, right? What we did is basically we created these buckets using VOG scores. So as I said, for a given testing data set, you can always calculate the VOG scores in inference time. And then what we did is we sorted all the images according to their VOG scores. And then we we calculated their misclassification rate. And what we observed is like for data sets like CFAR 10, we saw that images having low VOG scores are usually misclassified with less probability, but images having high VOG scores, which are basically hard examples, are often more misclassified. This trend is actually much more smoother for complex data sets like CFAR 100 and ImageNet, where we see some kind of a progression as you go from low VOG to high VOG, and we see the misclassification rate. So task 4 is basically about effectively using VOG as an unsupervised auditing tool. And I think we talked about this briefly when we were talking about VOG during calculating using inference time. So all the things that I've talked about is good because we had the ground truth labels in our training data set. But what about in a real world setting where we don't have the labels? What we showed in our paper is that we can calculate VOG exactly the same way, but instead of backpropagating the loss from the true label, we simply backpropagate using the top one predicted label of the model. And surprisingly, what we found is VOG works even in this setting. So if we closely look at these images, then you would see these images mostly comprises of test images. So this was on the ImageNet validation data set. So that's like the data set that people use to report ImageNet accuracies. What you see is most of the images are either misclassified by the model, and these are all the set of high VOG images, right? So you see this image was misclassified, again, misclassified image, misclassified image. And there are some images which are again either occluded or very unclear, like where the object is, right? So those are basically comprising of the high VOG images. Great. So working off the latter point where I just said that it can also be used in inference time, we then went one step forward and we said, can we actually use VOG as an out of distribution detection algorithm? And what we essentially did is we benchmark a few of the out of distribution data sets and we checked whether VOG can be used to identify out of distribution examples, right? Here we used MNIST-C dataset, which is one of the widely used datasets for doing out of distribution detection. What we showed here is that VOG is competitive while also being very efficient to compute. Now, what we see here is it beats most of the vanilla algorithms, but it underperforms the algorithms like autoencoder and autoencoder GAN. One of the advantages I would say for VOG, vanilla VOG in that sense is it doesn't need any pre-training per se. So in autoencoders and GAN kind of networks, in order to do outward distribution detection, one has to usually train those models on the in-distribution dataset first. And then they can use the learning or the embeddings to detect out of distribution examples. But in our case, VOG, what we essentially showed is that we don't need any kind of new training on the data set. We can just calculate the VOG scores as we did before and use that to get the out of distribution detection.
Okay, before you finish, there's a question. What exactly is out of distribution data set?
Okay, great. So basically, think about this like if you're a simple example of out of distribution data set can be that your initial data set on which your model was trained on is comprising of all clean images. But when you test the model, you're basically having images which were taken in real world from the wild, and it can comprise of some noises or it can comprise of some like multi-objects for the same class, right? So those kind of images are essentially out of distribution, basically the distribution on which the model was not trained on, in simple terms.
Exactly. I hope that answers your question, Avi. There's one other question that says, are you using pre-trained backbones while computing VOG?
Okay. If you mean pre-trained backbones, if you mean pre-trained models, then we can do that if we have the checkpoints for those models. So we don't care whether the model was pre-trained or we are training it from scratch. What we essentially need is just the checkpoints and the data set. That's it. We don't need information about anything else.
Right. Interesting. Okay, great. I think we can. And one last thing, when you were showing the images that you created, when you calculated variance of gradients, the single channel images, they did, like the first question that strike me was that are they not similar to latent representations that an autoencoder generates? So I can imagine why AE and AGANs perform a bit better.
Yes, I mean, again, because they have that distribution knowledge explicitly embedded in them, right?
Okay, we can go ahead, I think.
Great. So yeah, in this slide, it's not like a different task per se, but here we basically try to show that VOG is a stable ranking metric. And by that, I essentially mean that we trained a model on CFA 10 and we with random seeds, right? So it basically random weight initializations. We trained 5 different models, and then we plotted the VOG scores and showed the misclassification error rate that I talked about in the previous slide for all the 5 different runs. And for all the 5 different runs, we found out that the VOG scores have a similar trend, right? That for lower VOG scores, misclassification rate is lower. And for higher VOG scores, images, the misclassification is higher. Great. So yeah, in summary, in this paper, we basically present the variance of gradients, aka the VHG score, which is an intuitive proxy metric that builds on how the gradients change as the model learns. We show that it is efficient to compute as it only uses the vanilla gradients from training. It is stable, and it can be also, it can give us multiple views into the training dynamics of our model, right? One thing that I would like to highlight, and this has come up, I think, in a few of the comments when presented this paper, that VOG is both model and task agnostic. So as you can see, I never had any understanding or like any restriction about the model that we were using. We basically just needed a gradient. We don't care whether it's a ResNet or an AlexNet or a DenseNet per se, right? And we're not bounded by the classification task itself. If we have any supervised learning task where we can calculate the backpropagated gradients from a given label, then we can do it. It can be an image segmentation, it can be an image classification, right? Yeah. Maybe to summarize, we also have like an open source VOG scores for MNIST, CFA 10 and CFA 100 datasets in a Jupyter notebook, and I think I've added the link here. So feel free to explore it, and yeah, we also welcome feedback on the same.
If you can send me the slides after the talk, I'll put the link in the YouTube upload so that people can check out the videos.
Sure. Sure.
There's also a question in the chat. Naren is asking, how does VOG compare against uncertainty estimation techniques like MC dropout and assembly?
Right. So in terms of uncertainty estimation, I would like to highlight that we basically wanted to come up with a metric which is both interpretable in the sense that it were using explanation methods, like vanilla gradients in this sense, and you can also use like other gradient methods like smooth grad and integrated grad as some knowledge to calculate VOG. So that was the main driving point in this work, and we wanted to show that all the different tasks that you can do using VOG. So we didn't compare it with like uncertainty estimation techniques like you mentioned, but yeah, that was basically the motivation of this paper.
Great. There's a thank you, and there's another question regarding out of distribution. Did you do any experiments on datasets like ImageNet A, ImageNet R, ImageNet LV, etc.?
No, I think we just did works with MSC, and because again, as I said, we just wanted to show all the different tasks that you can do. But yeah, I think that's a great idea to get more robust understanding whether how good VOG is. We have to scale these experiments to larger data sets.
Exactly. And to be honest, let me get to the name. Kanjar. Yeah. I have been exploring ImageNet A, ImageNet C and A and all of these, but the real domain shift actually doesn't come with CIFAR 10 to CIFAR 10C. It's like, for my experiment, CIFAR 10C kind of adds like augmentations to CIFAR 10. So if you want to try something more challenging, switch to Vistari or switch to DomainNet or datasets that are actually very different to each other. Still, the distribution is same though. Okay, there's another question for you. Did you try to use VOG in curriculum learning and as a metric to define hard samples? What is the advantages of VOG compared with the loss?
Right. So with respect to curriculum learning, this is something that we have, I think, talked about in our conclusion in future works, that this can be actually one technique to do help curriculum learning per se. And as a metric to define hard samples with loss, again, I would like to highlight that there have been works which use, let's say, the prediction probability itself as a measure to determine easiness and hardness. But we did some experiments which are in the appendix of the paper where we showed that they don't work that well for these tasks as compared to VOG. And again, the interpretability point is always there.
Okay, there's another question. Continuing the previous question, will it be able to classify and get the VOG score for an image that can be an object of two different labels?
Sure, I think we can do that. For, let's say, you have one image where you had two birds from two different classes. You can always backpropagate, and if the model has learned or is learning about both the birds separately, then you can always backpropagate using individual labels separately and get those respective gradients out of them.
And you haven't had a chance to explore them in segmentation settings, right?
No, we didn't.
It would be interesting. It would be very interesting. Okay. So just feel free to put your, I think that's the end of the session that we had. Feel free to put your questions here. Till then, I want to ask some other questions. So yeah, how long did this whole collaboration and VOG take to form up? Were you already working on something around gradients earlier?
So I already started working on XAI before this project. So that was one of the motivations to come up with this idea here.
Okay. And how long did it take to complete the paper?
So there were different intermediate deadlines. So I think to wrap up the paper, I think we were able to do it in, I'm not sure, the first draft of the work was at least done in 3 to 4 months, if I'm not wrong.
Okay.
We were able to submit it to a workshop. Yeah.
Oh, wow. Okay. That's great. Yeah. Good collaboration. And regarding collaborative effort, I have been following MLC and it's been really active and the collaboration going on is great. But how does it actually, what tips do you give to work in a collaborative setting where you're not bounded by deadlines? You don't have a pressure to work on a project. So it's going to be completely on an interest basis. How to find right people who don't, like I have been parts of groups which loses momentum in some time and eventually we don't finish the work. How do you manage to work with that?
So I think that's like a case by case question, to be very honest. But with respect to deadlines, I think if there is a good collaboration and everyone in the team are on the same page, and the person who is actually doing the work, like the student or the researcher who is doing the experiments, doing the thinking and everything, if they are motivated to submit this or have a good deadline for them, then I think that basically extends to all the other people in the collaboration team. But someone, I think, has to take that step and be there to say that, okay, we should have a deadline for this. You cannot keep on working on this for 1 year or 2 years, for say. And I think in 1 year itself is a long time in today's machine learning research. So
that's true. 1 year is a very long time and there's a lot of incremental work going on. So your idea can be published way before you can even think to start writing about it. So yeah, I get it. Okay, that was a great talk. I think the audience was great.
Yeah,
okay,
hi, Chirag, I have a question.
Sure.
So can you talk about the comments from the reviewer side? Did they talk about any potential applications of using this VOG, or what are the takeaways from reviewers' comments? So
I think.
So what can be potential applications which people have suggested you that can be their VOG can be applied?
So few of the things that VOG can be applied, I think we already talked about in the presentation. In addition to this, I think someone also brought the point of curriculum learning, but this can also be used in active learning. Another thing that we wanted to explore, but we didn't end up doing it, was how to leverage VOG on the fly during the training process. So if you're, I think we were thinking to come up with an optimization algorithm using VOG, where we basically use the VOG scores as a weighting technique to upweight or downweight examples during the training itself, so that the model can focus on harder examples first as compared to easier examples. So yeah, those are like some of the ways you can extend this VOG paper, and also on different tasks. So I think there were questions when we posted this on Twitter. There were questions of whether we can do this on segmentation, whether we can do this on NLP tasks, right? So yeah, I think it should be extendable to those things.
So one other question I had is that regarding calibration of neural networks. So ideally, does that mean that low VOG values lead to overconfident samples? Can we use that as a proxy to find the value low VOG samples as the overconfident predictions?
I am not sure about if you're talking about by overconfident, if you mean samples that are memorized by the model, then yes, I think so.
More like higher entropy, right?
Yeah, higher entropy and overconfident mistakes. Like it is like the images of a class, it's a dog, and we are confidently predicting that it is a cat. So overconfident mistakes.
So I think that is something that we already showed, few examples, that if the images are misclassified, then those scores are actually high rather than being low. So the misclassification examples are usually examples with high VOG scores.
Yeah.
So high VOG is directly proportional to high entropy, which is directly proportional to miscalibrated predictions for you.
Prediction.
Yeah, how I understand it. Okay. There's one more person raising his hand, Karthik. I'll let you unmute yourself. You can go ahead.
Yeah. Thank you so much, Chirag, for a nice talk. It's really interesting to see how VAG can be used to identify the hard or the easy examples. My question is with respect to the unlabeled setting. Can we use this VOG as a measure to identify the hard samples as a subset, as a training subset in the transfer learning setting? So can we just use them as a training samples, and then can we try to annotate only those hard examples and train the system and evaluate it? So have you tried any experimentation in this direction?
So this is like a work under submission, so I won't be able to talk about it much. But what I can say is hard subsets can be actually used effectively to improve transfer learning. And what we basically checked is that even if you calculate the transferability thing on just hard subsets, then the model actually approximates that transfer learning accuracy of the student model better by using just harder examples than using the whole data set.
Okay, sure. Then maybe in future computer vision talks, maybe we would like to hear about your analysis on that part as well.
Sure.
Okay, I'll follow up.
Thank you. Yeah, thank you.
Okay, great. Nice. We now know for what work we have to invite you again. So it was a great talk, and I'm amused. Like VOG sound and seem to be super simple but so significant. So it's interesting. It's interesting, and it's not super compute expensive as well. So I would like to see how it pans out for different tasks, segmentation or test time adaptation, as I can see Nikhil seems to extrapolate it into. So thank you so much for this talk and agreeing to be with us today and so patiently answering all our questions.
Thank you. Thank you for the invite, Shambhavi and Nikhil. Thanks.
Great.
Thanks, Shira.
Have a great day ahead, great weekend, and we'll see you soon again. Bye-bye.
Thanks, guys. Bye.